What is this? Ugh. We're here looking at electrostatics. We're going to look at a Coulomb's law example here. This example is tucked under the E&M example handouts, electrostatics, Coulomb's example. And it's the first one that we're actually going to do for Coulomb's there. Now, in this example, if you don't have access to the Google Drive, it's sitting right here. You can just pause the video and take a look at it. But we have our 3-point charges, A, B, and C, and they're sitting on an x-axis, so they're all in the same line, at x equals 0 meters, minus, the minus is up here, 0.05 meters, and positive 0.04 meters respectively. So to kind of give you an idea of the setup here, it's going to go A at 0, B is going to be back here, and then C is going to be up here. And because this is at like negative 0.05 meters, you know, that is 0.05 meters, and because C is positive, forward on it, it's 0.04 meters here, okay? What we're going to do is we're going to calculate the magnitude and direction of the electric force on each of the 3 charges when the charges are 5 microcoulombs, negative 4 microcoulombs, and 3 microcoulombs. And let's really just do this. Let's just, instead of doing it for all 3 charges, let's just do it for charge A. Because if we do this for charge A, charge B and C follow similar principles. Let's just save a little bit of time here, okay? But what this does mean is because we do have the charges here, I like to do positive charges in red. That's just my shtick. So here's the A charge. It is a positive 5 microcoulombs, which is times 10 to the negative 6th. B is a negative 4 microcoulombs, so it's going to be over here. I like to do blue for my negatives. So negative 4 times 10 to the minus 6th. And C on the far right in the same x-axis line is 3 microcoulombs, so that's positive 3 times 10 to the minus 6. And these are all coulombs because the minus 6 is there. I'm just going to ignore the units for a little bit because I know they have to be charges. Okay, so there's QA, QB, QC. Now, if we want to find the magnitude and direction of the electric force, we need to use Coulomb's law. And if we want to do this for charge A, the sum of the forces, we need to remember that to find that net force, that is the sum of the forces. And we need to remember that forces are vectors, which means they're going to add a little differently than just regular numbers, okay? Because for a regular number, if I say 3 plus negative 2, we'd get 1, because that's like 3 minus 2. But in our case here, if we do that, we may find ourselves in a bit of a sticky situation, so we're going to have to be a little careful. Because we need to be a little careful here with these vectors, what I like to do before I even get into Coulomb's law is I like to write out and draw myself on this picture the direction each of these forces are going to act. So if I consider charge A and charge B, the middle and left charge, they are opposite charges. We know that opposites attract, which means that B is going to be pulled to the right from charge A. That's the force on charge B from charge A. And we know that charge A is going to be pulled to the left by an equal amount. These are equal and opposite forces. That's Newton's third law. And we'll call this the force on A from B. Fab. So that's what's going on between A and B. If we take a look at what's going on between A and C, these are similar charges. They're both positive because they're going to repel. They're going to move away from one another. So C is going to be pushed to the right. We'll call this the force on C due to A. And A is going to be pushed to the left. This is the force on A due to C. Now it may be the same or greater than the pink one here. I don't know. We haven't run the numbers yet. But it is going to go to the left. Okay? So this is important because now we know both of our forces here acting on A are in the same direction. When we add them together as vectors, we are going to add them to the left and then to the left again. And our resultant vector will be a larger quantity. So we need to keep that in mind whenever we're finally getting our final answers here, okay? Now to do this for Coulomb's law, we note Coulomb's law is F equals K, the Coulomb constant, 9 times 10 to the 9th, and then Q1, Q2 over R squared. Where in this case, Q1 and Q2 would be like A and B for the first force, and then A and C for the second force. If we wanted to see the difference, or the force between B and C, we would just use charge B and C with the corresponding distances for R. So let's first just do this for the force on A due to B, which is the same as B to A, just opposite directions. So we know this is going to be K, which is 9 times 10 to the 9th Newton meter squared per Coulomb squared. And then we'll make Q1 charge A, so that's going to be 5 times 10 to the minus 6th, because that's microcoulombs there. And this is a little trick I like to employ, and I think it'll make all of our lives a little bit easier. I do recognize that charge B is a negative charge. But remember, this negative here on the charge, when I put it into Coulomb's equation, the only thing it is telling us is that if our forces are negative, we're going to have attractive forces, and the particles are going to attract. I already know they're going to attract, though. I drew it up here in the diagram, okay? The only thing that the negative will do down here will possibly make my life difficult in the mathematics later. I'm going to ignore the negative, okay? I'm always going to ignore the negatives when I do this. I know it's going to seem a little weird. You're going to be like, well, can you do that? Trust me. Trust Lord Restob. So, ignoring the negative, 4 times 10 to the exponent of negative 6 coulombs. That is our charge B. Then we simply divide this by the distance between in meters, which is 0.05 meters squared. Now we take our trusty calculator that we've had since the year 2007, and we work that out, and we find that this is approximately 72 newtons, okay? It's positive simply because I've ignored the negative, but recognizing from my diagram, we drew this such that this force here is acting to the left. That was the direction of our force vector. If we do the same thing for the force on A due to C, we still have the K, 9 times 10 to the 9th. Force A is the same, 5 times 10 to the minus 6th. And force B, or force C in this case, the last force, is 3 times 10 to the minus 6. We didn't have to worry about positive or negatives because it was a positive charge, so who cares? We divide that by the radial distance between them, so that's 0.04. Don't forget that squared. And whenever we calculated this out, we find that this is going to be approximately 84 newtons, also pointing to the left. If I have a force of 72 to the left, and I add to it, to the left, a force of 84, my total net force from the start to the finish is going to be 72 plus 84. I'm going to get 156, oops, that's a 4, 156 newtons out of this. That is the net force on charge A. It's being pulled to the left by charge B, and it's being pushed to the left by charge C. Because they're both going to the left, I add them together. You'll probably recognize now that the mistake I could have made here is if I would have put the negative in for my negative 4 charge for charge B, then I may have accidentally put the negative here. There's nothing wrong with that negative. Mathematically, it looks right. But what I'm saying then is left is the negative direction and left is the positive direction, which that doesn't make any sense. And if I would have accidentally done that, I would have said, oh yeah, 84 minus 72, that's 12. And I think you'd all agree with me that 12 is not equal to 156. So that's why I omitted the negative there. It makes the math easier in my opinion because you're not carrying around things. And because we drew this picture early on, we have a much better idea of what our true final answer should be over here. Okay? So that was part 1 of our example. In our second part, we're going to take these exact same charges at the exact same distances, but we're going to rearrange them into a triangle and see how this changes up a little bit. But until we get to that, for now, we are finished. Take it easy. Adios.